In this video, we are going to discuss about sense-amplifier based register. So far, we have discussed two fundamental approach for building this age triggered register. One is using master and slave concept. Next one using glitch technique. These are the two fundamental approach for building the age triggered registers. So here we are going to introduce another technique which uses the sense amplifier structure in order to implement this age trigger register. Okay, what it will do means the sense amplifier it will accept small input signal, okay, and amplify them to generate rail to rail swing. That is minimum to maximum swing. Okay. So these are used mainly in Americos. And it is also used in low swing bus drivers to amplify small voltage swing present in heavily loaded circuit, loaded wires. So here there are so many techniques to construct this amplifier with the use of feedback, that is cross coupled inverter. That is a common approach we will use. So here you can see this circuit of the sense amplifier based register, and these whole circuit is called as front end amplifiers. Okay, so this whole part, okay, is known as front end amplifiers. Okay, so it samples the differential input. Okay, what it will do, it samples differential input signal on the rising edge of the clock signal. So the output of this front end is given to the NAND gate. Okay, cross coupled SR flip-flop. Okay, this SR flip-flop is formed basing using the NAND gate. Okay, so it will hold the data and guarantee that the differential output switches only once per clock cycle. Okay, so here the differential input in this implementation doesn't have rail to rail swing. Okay, So therefore this registers it can be used as a receiver for reduced string differential buses. Okay. This M5 transistor and the M6 is called as cross coupled inverter. Okay. M5 to M8.
Okay, taking that one first view.
Sorry, M5 and M8. Okay, we can see. So this is a cross coupled inverter. And this is L1 and this is L2. Okay. So what happens when it is in pre-charge state? Pre-charge state means clock is 0. Okay, if clock is 0, this M9 and M10 transistor get turned off. Okay. So as a result, this M7 and M8. Okay, this M7 and M10. M7 and M8 is during the clock, when clock is 0, M9 and M10, right? M9 and M10 is on, and whereas M7 and M8 is off. Okay. So if it is turned on, this VDD will goes to L1 and L2, right? So L1 and L2 values becomes 1. Okay. So if L1 and L2 value is 1 means that will go to my S and R. So okay. So if S and R is 1 means so output is equal to previous state. So it is nothing but a whole state. So what is this this SR logic means 0 0 0 1 1 0 1 1. Okay. This is Q plus. So this is nothing but this is invalid state. Okay, invalid, and this is 0 and this is 1 and this is previous state. Okay. That is Q. Okay, it will hold the value. So when clock is 0, it will hold that value. Okay. So whenever the clock is 0 means this M1 transistor. This M1 transistor is off, right? So M1 transistor is off. So this is about the pre-charge state. So what happened to my evaluation state? Okay. So whenever the clock is 1, this M9 and M9 and M10, right? M9 and M10 is off, right? M9 and M10 is off, and the M1 transistor is on because it is in the evaluation state. Okay. So I'm going to give a differential input. Okay. So on the rising edge of the clock, the evaluated transistors turns on. The differential on the differential pair, that M2 and M3. So I'm going to give M2 and M3 as 1 and 0. Okay, 1 and 0. So if 1 is given to the NMOS means M2 is on and M3 is off. Okay. So, and the difference between the input signal is amplified on the output node on L1 and L2. If the invalid is 1 means, okay, this is 0. Okay, if this is 0, so this two transistor M2 and M1 is on. So M2 and N1 is on means this will pull this value of N1, right? So the L1 value get pulled to towards ground. Okay, since this is on, this value, entire value will, you can see this value is also 1, right? If this value is also 1 means this transistor, that is my M5. Okay, M5 and M6 is on, right? M5 and M6 is on. Okay, so previously it is in the value of 1, right? Previously it is in the value of 1. Okay, the 1 get pulled to 0 because this transistor is on, this transistor is on, this transistor is on. So this value get pulled to 0. Okay. So since this value is 0, this value will make this transistor off. Okay. So this value will make me M6 off. M5 is on and M6 becomes off. If M6 is off means so this will hold the same value, right, as 1. So now S becomes 1 and R becomes 0. So my output is S is 1 and R is 0. So therefore my output is 1. Okay. It is vice versa when I connect in as 0 and in bar as 1. Okay, this is what I have explained here. So if I give 0 and 1 for in bar, this tends to get turned on and initially these two values are 1, right? So initially this these values are 1, 1. Okay. So initially this value is 1, 1. So what happened? This 1 will make my this transistor to turn on. So my initially it is 1. So 1 will go to 0. Okay, this transistor is on, this transistor also turned on, and this transistor also turned on. So the 1 becomes, it will goes to 0. If it goes to 0 means this transistor goes off. Okay, so whatever the value 1 will remain same. Okay, here. So this, so here M6 and this is M5, right? So here M6 is on and M5 is off. Okay, and here in bar is 1 means since in bar is 1 it is off. Okay, and in bar is 0 means this is off. So in equal to 0 means this is off. So you can see 1 is going to 0. So therefore here also this one goes to 0. Okay, so if it is 0, this is S and R. So if this is 0 and 1 means output should be 0. Okay. So whatever the value in will reflect in the output. Okay. So you can see during the this is my clock. Okay. Whenever the clock is 0, the clock is 0 means it is a pre-charge state. Okay. It is in a pre-charge state. So S and R is equal to 1. Therefore, my output will hold the value, right? Output will hold the value, hold the previous state. So whenever the clock is 1, it goes to the evaluate state, right? So evaluate state means whenever it will check the value of input, okay, IN. So if the IN value is 1 means if the IN value is 1 during the we are giving the clock as 1. So you can see it will work as a positive edge trigger, right? Positive edge trigger. Only during at this point, if the in value is 1 means it will reflect in the output. Output as here you can see the in value is 0. So the output value is 0 during the positive edge of the clock. Okay. So what happens again if I change the value of the input? So here you can see first you can see for the input during the evaluation phase when the input is 1, IN is 1, output is 1, right? Output is 1. Okay. So during the evaluation phase, next value I'm going to change this 1 to 0. Okay. If I change 1 to 0 means the output should not go to 0. Okay. It has to hold that value because it is working as a positive edge trigger value. It is not a positive latch. Okay. So let's see this one. So this is my so I have removed this M10 and M7 transistor. Okay. So this is same as this one. Okay. So I have removed this portion and this portion. Okay. These two transistors. Okay. Since that we are working in the evaluation phase. Okay. The clock is 1. So clock is 1 means it is in the evaluation phase. So if the evaluation phase means M1 is on, right? M1 is on. So this one is connected to ground. Okay. So initially we know that if input is 1 and in bar is 0 means you will have S value is 1 and R value is 0. Okay. Based on this. Okay. Input is 1, output is 0 means it is 1 and 0. Okay. So what happens if again I change the input? Okay. If I again change the input during the evaluation phase. Okay. So if this is 1 means what will happen? If this is 1 means this is 1, and if this is 0 means
Again.
okay, if this is 1 means this is 1, and if this is 0 means
Come to the Victoria field.
so here this one is connected to 0, so this is 0. Okay. And this is connected to 1, so this is 1. Okay. So what I'm going to do is I'm going to change my 1 value to 0, 1 value to 0 and 0 value to 1. Okay. So this should not reflected in my output. Okay. That is here the 1 should not get changed to 0 and 0 should not change to 1. This should not happen. Okay. Because it has to hold the value. Okay. Let's see whether it is happening or not. Okay. So you can see this now you can see this one this one will activate my M5 transistor. So M5 is on and M9, so can see the M9 is off. Okay, M9 is off. Because of this one, since the M9 is off, there will be a leakage current. Okay, there may be a leakage current. So this 0 get turned to 1. Okay, because of this leakage current, this VDD will reach here. So it will change to from 0 to 1. Okay, so this one, okay, this one will make my transistor this M6 turn on. Okay, so this one will make my M6 to turn on. Okay, if this one get turned on means my 1, okay, my 1 get turned to 0. Okay, this one goes to 0. Because why it is going to 0 means this transistor also on, and M3 is also on. M3 is also on, right? Is also on. So this will make my 1 to go to 0. Okay. So since this transistor 1 is on, this already it will reach the value of 0 of 1. Okay, and here this 1 of 0, it goes to 0. Okay. So you can see this 1 get turned on to 0 and 0 get turned on to 1. Okay, if this shorting transistor is not available, okay, this M4 is my shorting transistor. M4 is my shorting transistor. Okay, so you can see this is my leakage path. Okay, so you can see this will be in the high impedance state. Okay, so if I include this shorting transistor, okay, so whenever if I include this VDD, that is M4, M4 is always on, right? So always on. Okay, since it is always on, there will be a path from for this one to go to ground, right? Because this one, since M4 is turned on, it will follow this path, then M3, then it will reach the 0 value. So if it reaches the 0 value means, okay, so this is 0, okay, since this is get turned on, right? If you see, if I change this if I change this 1 to 0 and 0 to 1, okay, already it is in 1 to 0, okay, this one will make my transistor to turn on, okay, though it will go from 0 to 1 due to the leakage, okay, since it is turned on, this one will again go to 0, okay, from following this path, okay. So though I have a leakage, okay, this one value is going to ground, so the 0 will remain as same, okay. So the whatever the change, that is 1 to 0 and 0 to 1 will not reflected in the output. That is 1 is not changed to 0 and 0 is not changed to 1. Okay, so this is the use of this shorting transistor. Okay. So let me explain this. So this shorting transistor M4, which is used to provide a DC leakage path from either node. L3, this is my L3 and L4 to L3 or L4 to ground. Okay. So this necessary to accommodate the case where the input changes their value after the positive clock edge has occurred. So which will resulting in either the L3 or L4 being left in high impedance state with a logical low level value stored on the node. So without this leakage path, that node will be susceptible to charging by leakage current.